All right. Well, hi everyone. Welcome back to the Theory of Computing for Fairness, the seminar series. This is actually going to be our last one of the semester. So our speaker today is Sean Sinclair. He's an assistant professor at Northwestern University right now in industrial engineering and management science. Before this, he was a postdoc at MIT, and before this, he actually did his PhD at Cornell University, where he was advised by Christina Lee and Sid Banerjee. He does like a lot of research on developing algorithms for data-driven sequential decision making with like a lot of societal applications and problems. And today he's going to be telling us about his work on energy efficiency trade-offs in dynamic fair allocation. And I tell you,
Great. Yeah, thank you so much for the introduction and for having me. So I'm excited to be here to talk about a recent line of work that I have on NV efficiency trade-offs. The majority of this presentation will be based on a paper that I have with my co-author Sid Banerjee at Cornell and then Shamsi Hussain, who's at USC Marshall and also in the audience with us today. And feel free to interrupt and ask any questions as you wish. To start off, I want to first mention and give a little bit of context into this problem. So, this line of work is motivated by a partnership that I established during my PhD with a local food bank, which is the Food Bank of the Southern Tier, which is local to Ithaca, New York, where I went to graduate school. And more broadly, these kind of food bank programs across the United States, they partner with Feeding America, and their kind of goal is to provide food to low income people across the region. And I want to emphasize that their high order goal is to provide high quality and also fresh food. And the impact of freshness will be an important consideration throughout this presentation. In fact, the Feeding America is a really large distributor of food across the United States. They distributed over 5 billion meals through their networks 2 years ago. And more recently, there's been a growing interest in the operations community on studying mobile food pantry models. And this consists of a physical truck that's pictured here, and it's loaded up at one of their depots. And it then travels to different underserved areas in order to provide food. And it'll spend maybe a couple hours at each location distributing food and then moving on to the next, then returning to the depot at the end of the day. And from working with them, kind of what they wanted to understand is how they can design these allocation mechanisms in order to allocate resources that balance notions around fairness and efficiency. And we'll see that these two metrics are in direct tension with one another throughout this presentation. For instance, a solution which is fair could be to allocate nothing. And it's fair to some extent because everybody is treated the same, but it's obviously not efficient because none of the resources are getting allocated. Similarly, an efficient solution would be to give everything to one person. That's obviously not fair, but the resources are getting used. So, to some extent, such a solution is efficient. And the reason that balancing these notions of fairness and efficiency is challenging is kind of twofold. So, the first issue that comes up in operating these systems is around demand uncertainty. So, here on the right hand side, I have a picture of the southern tier of New York, which is an upstate or the Finger Lake region, along with little indicators for all of the different distribution locations for the food pantry. And the way that they operate their program is they have a prefix schedule that's posted in advance, approximately a month or so. And this dictates the series of visits that this mobile food pantry is going to take on that given day. So it's going to start off in Horseheads and then continue to Watkins Glen before then heading over to Ithaca. And this mobile food pantry schedule is fixed in advance. And then throughout the day, as the food pantry is traveling to these different locations, volunteers at each location are making an irrevocable decision on how much to distribute before moving on to the next location. And so, because of this, the food bank doesn't know how many individuals are going to show up to each of the future locations beforehand. And this creates this form of tension or challenge where they need to conserve enough food for later sites. And you might have this question of why don't they just have people call in? And indeed, food banks have often thought about this, then demand would no longer be uncertain, obviously. But the issue is that customers often like the flexibility to kind of choose which time and which location and which distribution site that they want to visit for the food pantry. The second issue, which will be the kind of core focus of this presentation, is around food perishability. And this is a large interest of these mobile food pantries, going back to their goal, which is to distribute fresh food. For instance, the Los Angeles Regional Food Bank distributed 25 million pounds of produce 3 years ago. However, it's well documented in their operating reports that managing fresh produce is actually a big challenge. And actually, a lot of food banks across the country don't even receive perishable food because it's tough to keep spoilage under control. And you can see firsthand what happens when you don't. For instance, there's this article from the LA magazine asking why Los Angeles is tossing food for its homeless population in dumpsters, literally right next to a lot of the homeless encampments in the city. And the challenge that comes from perishability is that holding onto produce for too long leads to waste, right? Because the food is going to perish. However, you want to allocate it fast enough for efficiency, but that counterbalances your fairness goal as well. And so this kind of creates this key trade-off where running out of food too early is unfair because later locations do not receive any food, but it's efficient because you're allocating the food. And saving too much for the end is inefficient because it could potentially lead to waste or spoilage, but it's fair because you're able to treat all of the different locations similarly. And so here, what I'm going to present to you is kind of like a simplified model with a single resource, a single type of customers, and linear preferences. This is mostly for the purpose of this presentation. In the paper, actually, we consider a more complicated model with multiple resources and multiple customer types and potentially nonlinear utilities, and happy to talk about that more offline. And so here we have our simplified setup. So we have this mobile food pantry on the left-hand side, and it's loaded up with a fixed budget of resources. Here we have 8 bundles of vegetables that it's going to allocate across 4 different periods, which are located on the x-axis at the bottom. And then in order to model resource perishability, we are going to assume that each of these bundles of vegetables on the left-hand side, so each unit B, has associated with it a stochastic perishing time, which we will denote as TB, that's drawn from a known distribution. However, these perishing times are not known to the algorithm in advance. For instance, you only know once an item has perished once it's actually perished. However, you do know the distribution in advance. And so because of this, we're going to assume that the algorithm has access to a prediction of what the perishing order is going to be, which we'll denote as sigma. And you can think of the sigma as some ordering as to the order that you're going to allocate these resources. On the left-hand side, we're allocating from the top to the bottom in order. And you could think of organizing these according to like the expected perishing time. And at the end of the presentation, I'll talk a little bit more on the design of this perishing order. But for now, you could just think of it as like increasing in order of the expected perishing time. So that deals with the resource perishability piece. Next up, we have to deal with the demand piece. And so at each one of these locations on the bottom, we are going to assume that they have some demand for the resource, which we will denote as NT, and it's revealed at the start of that period. And again, it's going to be drawn according to a known distribution. Here at the bottom, the number of families at the first location is 3, second location is 1, third location is 2, fourth location is 1. And again, we're going to assume linear utilities. It's not important, but it's just to simplify this presentation. And again, our goal, design a sequence of allocations that achieve simultaneously high fairness and efficiency. And so I need to come up with a mathematical definition for both of these metrics. Okay, our first metric is inefficiency. We also call it efficiency loss or delta efficiency, measuring a difference to an efficient solution. I kind of use those terms interchangeably, and we write it as this delta efficiency term. It's computed as B minus the sum over the locations, demand for that location multiplied by the allocation, which we'll denote as XT_alg for the algorithm's allocation at time t. And this is going to be a per person allocation. It's going to be the same per person because we're assuming a single type of customer with linear utilities. But again, in the paper, we have a more complex version of the model as well. And what this does is it ensures that the resources are used in order to limit waste. And it also penalizes for spoilage. In this example on the bottom, the resources with the red X through them have spoiled. So for instance, this first resource here has a perishing time of 1. It was not allocated and spoiled. Similarly for the resource 2, and then for some reason at the end, the truck also has 2 resources left over. And so your delta efficiency is going to be 4 for the 8 minus the 4 that gets allocated here. And obviously a solution of 0, one that allocates all of the resources, say, to the first family, is somehow good in a sense because you're allocating as much of the resources as possible. So this will be our first metric for efficiency. And our second metric is unfairness, or difference to unfairness. I also do a lot of online learning work. And so I like to think of this as a form of regret benchmark. And so what this metric is it computes the maximum over all of these three locations here indicated at the bottom, the difference in the allocation that the algorithm made, which is xt, versus an idealized allocation in hindsight, which in the simplified model with a single type of customer and linear utilities, what you should do is just divide all of the resources equally amongst all of the customers. And so we're going to look at the difference against B over N, where this N without a subscript T corresponds to the total demand across all of the different locations. And so what this does is it promises to individuals to receive as much utility to what they should have gotten. And so here in this example, we have 4 families, 8 baskets of vegetables. So B over N is equal to 2. And your delta fare is equal to 2 because this last location, location 3, received nothing, whereas they should have received 2. Okay, so
Can
these are
you
going to
can
be our
you
two.
quickly, sorry, can
Yeah,
you go back to the other slide? I think I like lot. Sorry. So N sub T is the number of goods that were actually allocated at that time step.
NT is the
Um,
number of families at that specific time step, and then XT is going to correspond to the allocation that you made to those families. So for instance, in this first location, NT is equal to 1 because there's a single family, but XT is equal to 2 because we allocated 2 resources to that one family.
okay. So you get 4 because, sorry, I just thought that it would be 3, not 4. So I'm just trying to backtrack the numbers,
Yeah, so it's 4 because you started off with 8 units of
right?
these vegetables, but you allocated 1, 2, 3, 4. So for this first
Oh,
family,
okay.
N1 is equal to 1, but X1 is equal to 2.
Okay.
Whereas for
Yeah.
these families, N2 is equal to 2, but X2 is equal to 1 because we
Okay, I
allocated
got it.
one bundle
Okay.
per family. Gotcha.
Okay, thank you.
Great. Good question. Great. So with that, we've introduced our 2 metrics, and kind of the main contributions is we're going to trace these curves. So x-axis will be one metric, unfairness, y-axis will be another metric, and efficiency, and we're going to provide an exact characterization of the achievable pairs of these metrics. So we're going to trace off some of these curves, showing that anything above that curve for the Pareto frontier is achievable, and anything below is going to be unachievable. And this is kind of inspired by the price of fairness literature, spearheaded by Bert Seamus in 2011. And in doing so, we're actually going to be able to isolate the impact of uncertainty on this trade-off. So we're going to notice that there's going to be a vertical asymptote and a horizontal asymptote. These are fundamental lower bounds on these metrics. And we're going to show that some aspects of demand and perishing uncertainty are going to kind of be the main drivers of this unachievable region on the horizontal and the vertical asymptotes as well. And so with that, I want to touch upon some of the more closely related works. So there's obviously a long literature on fair division in the econ and computer science communities, with most of the work thinking about ways to allocate resources to satisfy some fairness conditions. And there's lots of different examples of fairness objectives, whether that be maximum utility, national social welfare, or group fairness guarantees. However, the majority of these works don't additionally study the impact of perishability on tops of these models. However, from an operations perspective, perishability is actually well studied in the supply chain and inventory management literature. It's been studied both on scheduling and also joint pricing and management decisions as well. However, I will say that often we found from looking at the literature, perishability is typically assumed with either deterministic perishing or IID perishing. And noticeably, we don't make either of those assumptions in this paper. And you'll see very soon why potentially often these papers consider these more simplified models because perishability kind of throws the wrench into a lot of the analysis that you might think of. So it's going to come out soon. However, I will emphasize that this kind of line of reasoning on understanding a trade-off between different objectives of fairness and efficiency has started to be studied, included by one of my preceding papers that we'll talk about as well. And kind of the main contribution of this piece that we'll be focusing on is providing an exact characterization of objectives, as well as explicitly modeling this depletion or perishability of resources that is really going to change the way we have to model and think about this problem. And so with that, the rest of the presentation is divided into 3 different segments. So in the first segment, we're going to talk about this condition called offset expiring, which is going to serve as some form of lower bound on when low NV is even a feasible solution. Second, we're going to characterize the feasible regions. So we're going to trace out that curve, which is the necessary loss due to demand uncertainty. And we're also going to see it comes from errors in the perishing order. And third, we're going to propose algorithmic guardrails. This is this algorithm that's going to achieve this trade-off curve that we've established before. So first off, we have to start off with perishability. So I want to give you a little kind of a simple and stylized example as to why this unfairness metric where we compete against B over N is difficult, even against a no perishing solution, and even if we had full information. So we're going to consider this kind of stylized example. We have 4 bundles and we have 4 families, and T is equal to 4. And so B over N, their solution, your fair solution in hindsight, is equal to 1. However, we are going to assume that all resources perish after the first time period. And so what that means is as the truck continues, it's able to allocate the first resource to the first family, but then in the second, third, and fourth families, well, those resources have perished, and so they can't get anything. And so it turns out that under any allocation strategy, your unfairness is equal to 1, no matter what you do. And that's simply because your perishing process is really aggressive. Like perishing is happening incredibly quick to the point that to some extent there's no point doing anything because everything expires after the first period. And so a kind of takeaway you should get from this is that there has to be a lower bound on unfairness that measures kind of like the strength of perishability, right? You should have no hope of getting a low performance metric for unfairness if your perishing process is aggressive. And this is even under a model where we assume that we knew the order, we knew the demands, we knew all of the resource perishing times. You're just fundamentally unable to allocate the resources before they perish. And so you might think, okay, what if it were to happen if we were to kind of reduce the rate at which these resources perish? And what is the kind of slowest rate possible for which in hindsight you could still achieve and allocate B over N? And so you could relax this to instead say that exact same setting for resources, demand of 1 per location. However, the perishing times are going to be done exactly in order. So the first resource perishes after the first day, second resource after the second day, third resource after the third day, and fourth resource after the fourth day. And here, if you were to allocate in order, according to the true perishing order, you would have an unfairness of 0 because everyone's allocation is equal to 1, and the hindsight optimal B over N is also equal to 1. And so one of the contributions in the paper is kind of quantifying exactly what this looks like what is a necessary condition on the perishing process so that if you had perfect information, you could achieve an unfairness of 0. And the kind of high-level picture of this result is that proportional allocation is feasible under this hindsight perishing order, so long as the perishing process satisfies this condition, which says that the number of goods that perish before each time step is upper bounded by B over N, that's your fair solution in hindsight, multiplied by the demand before that time step. And this process at the bottom satisfies this as an equality because the number of goods that perish before T is equal to T, and B over N times the demand before T is equal to T. So it's exactly matched, right? And so it turns out that as well, if you had IED perishing, so like a geometric distribution for your perishing process, that in order for this condition to be satisfied, the probability or rate of your perishing needs to be at most on the order of 1 over T in order to satisfy this condition. And again, the intuition behind this is that the right-hand side, B over N times the demand before T, you can also write that as B over N times N less than T. That's the partial sum of the demand before T. That's the amount allocated under the proportional allocation before T. So it makes sense. That's the amount that the hindsight allocation would allocate at that period. The left-hand side, number of goods that perish before T, that's the size of the set of all resources B, whose perishing time TB is before T. That's the number of resources that perish before T. And so obviously those two need to be in order to be able to allocate that across each period. And so what does this kind of say? First is that without this condition, the algorithm has some lower bound on the performance of unfairness. However, this is full information. We are assuming that the algorithm actually knows the order in which the resources are going to allocate, which again, the algorithm does not. They only have access to a prediction. And so we're going to have to do something a little bit more complicated in order to quantify our lower bound. However, I want to take a second to say, okay, potentially there's some modifications in the unfairness definition that you could make. We're being a little bit stringent. We're saying a maximum over all time steps t of this deviation. Potentially, you might want to change into something that's a little bit more forward looking. And we've talked about that a lot and have some preliminary ideas. And if there's time at the end, I would love to chat about it more. But that's a fair comment. So great. So with that, going to move into the second section, which is going to be characterizing this feasible region or a necessary loss due to demand and errors in this perishing order. And so I've been kind of alluding to this curve in before. And so now we finally have the curve. And so the main contribution of our paper is shown here. So we're going to show under some standard regularity conditions on the demand, we are going to quantify some term, which we call L parish, which is coming soon. And we're going to show that any algorithm has some impact due to demand uncertainty, which says that your unfairness is at least 1 over square root of t. So that's your horizontal asymptote here at the bottom. Part of it is there. Second is a trade-off that's established in my prior work, which says that you can't simultaneously minimize both of the metrics. So the product of inefficiency and unfairness needs to scale at least as a constant. So you cannot drive both of them to 0. And so that's this y is equal to 1 over x curve that you see here. And then the third term is the impact of perishing uncertainty, where we will establish that this quantity, L parish, that we're about to define, exactly also carves out a vertical and a horizontal asymptote, showing that your unfairness is at least L parish, and then your inefficiency is at least t times L parish. And so the rest of the presentation will be talking about these 3 different results. So any questions here before I move on to going through the formal lower bounds? Or we're good?
Do you mind if I just spend 20 seconds just staring at the slide?
Yeah.
Thanks.
And so I guess kind of before continuing, I want to emphasize that the main piece of this work that we'll be discussing is this part on the bottom, which is the perishing uncertainty piece. This proof for the second one is a little bit technical, so I won't discuss it too much. But the high level intuition is that in order to drive efficiency to 0, you need to allocate a lot, but that penalizes you in terms of unfairness. So that's why they can't both go to 0. And we'll go through the argument for the first one. It's pretty simple. So.
I have
Sorry.
actually one quick clarification, or maybe you could
Yep.
elaborate on. So I was a little surprised when you introduced the motivation for like the perishability framework, because in my head I thought, well, this would like the fact that it's stochastic, I guess, because in my head I was
Mhm.
thinking, well, like we have sort of best by dates on things, and surely people would just be able to sort of like order
Yeah.
that and have knowledge. And then I thought, oh, okay, maybe that's not totally accurate because maybe like best by dates are in theory just suggestions. So maybe people are giving out produce and stuff after the best by date, or maybe things could perish before them if the truck is hot or something like that. So can you just like give me a bit more of the
Yeah.
context, I guess?
Great question. So this is about like why are we modeling stochastic perishing, and that's totally valid. In doing research, I learned a lot of very interesting facets about the U.S. regulation around food and best by dates. It turns out that there really is not really much of a regulation, and so first off, like our model is general, even though we say stochastic, like some of them could be deterministic if you have multiple resources, and the deterministic perishing time is just the sell by date. However, for produce or items like that, they don't have like specific best by dates. And so it's easier to think of perishing as stochastic for fresh produce. And that's typically what's considered in the operations literature is they assume that these perishing times are stochastic or there's some probability that they spoil within the next day. Um, and yeah, so it's kind of like we're considering fully general for stochastic as a way of kind of modeling both of those types of situations.
Okay, thank you.
And then also again, this presentation, we're only considering a single type of resource. But in the paper, we have multiple types for which some of them being deterministic, some of them being stochastic with different distribution makes a little bit more sense.
Okay,
Yeah.
great. Thank you.
Great. Okay.
Oh, sorry. Do you mind if I can
Yeah,
also
ask
ask a
away.
specific question? I'm looking at two right now. Is there a reason that you're looking at the product or the expectations, not expectation of the product?
So the reason that we look at expectations of the product is only for the lower bound, which you'll see in a second how it comes up. And the upper bounds, we do high probability for everything. Yeah.
Thanks.
Great. So in some prior work, so I have the title linked at the bottom here. I've established these two results. I won't talk much on the second one, but for the first one, I think it kind of clarifies the model. So for the first result, recall our definition of unfairness, maximum over locations, difference from allocation versus B over N. However, N, as written, is a random variable, right? It's a total demand, sum over all of the locations, demand for that location. And at the first location, you have the least amount of information about what N is going to be in the future. And so this quantity N as a random variable is going to be anti-concentrated by the Berry-Essen inequality, which means with constant probability, it'll be its mean plus square root of t or its mean minus square root of t. And because of this, at the first location, the best thing that you can do is shoot in the middle and allocate b over its expected value. With constant probability, you're going to be off above by root t. With constant probability, you're going to be above by root t. And that root t appears on the denominator. And so that's why you get a 1 over root t factor. And from this, you should ask the follow-up question. And all of these inequalities here should be squiggles because there's dependence on the range and the variance and things like that, which I'm not including here, but we have in the paper. So that's the main intuition for the first result. And again, for the second one, it's a little bit complicated, but it just kind of links back to this tension that you can't allocate too fast and you can't allocate too slow. And whichever one you do, and you end up hurting one of the metrics. Okay. So I want to spend the majority of the time focusing on this third piece, which says that any online algorithm has this term, which I've said so vaguely, L parish, it's not defined, such that your unfairness is at least that quantity and your inefficiency is at least that quantity. And you should say, hey, Sean, like literally 10 minutes ago, you just defined this definition. And you said, if your perishing process is offset expiry that satisfies this condition, you should be good to go. However, I put one specific thing bolded inside of this proposition, which is that this holds under the hindsight perishing order. So it assumed that the algorithm knew in advance the order for which the resources are going to perish. However, if you think about this food bank, it just has a box of bananas. It shows up at the first location. It says, these bananas look identical to me. I'm just going to pick one of them at random and allocate it, right? However, these bananas are going to perish at different rates, right? And so this condition is obviously not sufficient for thinking about the performance that the algorithm should have in these settings. And so, yeah, you should have this question of like, is offset expiry, this condition, sufficient? And the answer is clearly no, because the algorithm doesn't have access to this information in advance. And instead, they have to allocate according to a prediction sigma for which these resources are going to perish. And so we're going to consider this exact same model that we keep going back to. 4 locations, 1 family per location, 1 bundle of vegetables per location. And we're going to assume that exactly 1 resource perishes per time step. So it satisfies the condition had you completely reversed the order for which you are going to allocate these resources. However, we are going to assume that sigma, our prediction for the perishing order, is going to be completely reversed. Again, this is an extreme example. However, it helps to illustrate the ideas of what's happening here, right? And so what would happen if you do it? Well, the first location is good because their resource perishes at time 4. We visit them at time 1. Second location is also good because their resource perishes at time 3. However, when we get to the third location, that resource has perished. When we get to the fourth location, that resource has also perished. And so because of this, your unfairness is equal to 1, because locations 3 and 4 get nothing. It turns out that in this example, the best that you could do is to just take the first resource and split it equally amongst everybody, right? So you're giving out a lot, right? And you can quantify its unfairness in terms of 1 minus 1 over 4, because what they should have gotten is 1. Instead, what they're getting is 1 over 4, which is that split. And so you can show that this is actually the maximum NV-free allocation, which is everybody gets the same amount of the resource. And what this kind of means is that there's kind of two sources of errors that comes out in the perishability process. One source of the error is because it's happening really fast. The second source of the error is that you have errors in your allocation order. And it turns out that these errors are actually costly in terms of both fairness and efficiency. And what we saw in this specific example is it forces the algorithm to allocate less than B over N. So here, what you wanted to allocate is 1, but instead the best you could allocate is a fourth. And the reason is that if you wanted to allocate the same amount to everybody, 3 resources are going to spoil no matter what. And so because of this, you're forced to allocate strictly less than this B over N. And so this is going to get us starting into dealing with this entanglement between the rate at which these resources are going to perish combined with the allocation decisions made by the algorithm. And so this is kind of the main motivation and reason to study this idea on the kind of coupling between perishing and the allocations that the algorithm is making. And so, okay, we've gotten to this point where the quality of the perishing order prediction plays a significant role. Under this allocation order sigma, you can construct an upper bound on a time for which a resource is finished allocating as follows. And we're going to denote this time as TB, tau B, the time that resource B is finished allocating under the order sigma, if everybody receives the same allocation X. And you're going to see in a moment why we keep X as a decision variable. And that's going to be because we want to allocate the most so that we reduce efficiency that still satisfies fairness. Okay. And so a quantity to define this, it's going to be the first time, so inf over t, such that n less than t times x, this is the amount that's allocated to people before this location, is greater than or equal to sigma of b, which is the location of that resource in the specific allocation order. Or here we're using sigma like as a permutation notation. And so in this example on the bottom, if we were to allocate one resource, so our X indicator is 1, under this order sigma, then this first resource is finished allocating at time 1, second resource at time 2, third at time 3, fourth at time 4. However, if we, let's say, compare, we saw the third and the fourth ones were screwed. And the reason that they're screwed under this definition is that their perishing time is before the earliest that they could be allocated, right? And so you can quantify this exact mechanic by writing down this term delta, which measures the quantity of resources. So it's the number of resources B whose perishing time, TB, is before the earliest for which they could be finished allocating under X. And those resources are going to perish no matter what. And so in this specific example at the bottom, delta of 1 is the number of resources that have a perishing time before the earliest allocation time. That is going to be equal to 2 here, right? Because it corresponds to the 2 resources on the bottom shown. Okay? And then it turns out that any feasible allocation, so fixed quantity to all of the different locations, must satisfy this inequality here, showing that X is less than or equal to B minus delta of X over A. And so this shows that delta is exactly this kind of intuition that we established as this kind of necessary reduction in your allocation that happens both due to the rate at which resources perish, but also errors in your prediction order sigma. And this captures both of those terms because if resources perish really fast, then you can quantify that in terms of your delta because these TBs will be low. Similarly, if your sigma is really bad and miscalibrated, then your tau is going to be off. And so this delta term characterizes both of them at the same time. And this is kind of the meat of the paper here. It's quite complicated to think about because it's endogenous to the algorithm. It depends on X, the amount that you allocate. Also, something I didn't emphasize at all is that everything on this screen is a random variable. So TB is a random variable, n less than t is a random variable. Obviously, the algorithm needs to use this in some way, right? And so it required a lot of new concentration inequalities that we don't have time to get into. However, I will say that it recovers a no Parishchian solution when delta of x is equal to 0. So it kind of reduces to the old version of the paper. And then this is the reason that we have x as a decision variable, is obviously you want to allocate the largest amount that satisfies this inequality. And so this is when we can define our L-Parish term, which is the best static allocation is the largest x, which satisfies this inequality. And we refer to that difference between b over n and that solution as its loss that occurs from perishing. And this is a kind of fixed point equation, right? And so you can quantify it with a combination of these concentration inequalities. And in the paper, we have a lot of discussion about how can you quantify L-Parish, what does it look like under different perishing distributions, which if I have time at the end, I'll try and get to, but happy to talk about it more offline after the presentation if there's time. Great. And so now we've firmly defined L-Parish. And so this is exactly kind of characterizing the best that you could do in hindsight, because that's exactly how we constructed it to be. And so with this, our lower bounds that I hinted at earlier, showing that any Allen algorithm suffers expected unfairness of L-Parish and expected inefficiency of T times L-Parish. Well, the reason that unfairness is L-Parish is clear, because unfairness is b over n minus the allocations. The best you could do is allocate x lower. B over n minus x lower is exactly equal to L-Parish. And so that gives you the unfairness lower bound. For the inefficiency lower bound, this just happens because you have to underallocate by this amount each period. We have t periods. You sum it up over the t periods. And so your inefficiency loss is t times that quantity L-Parish. And so this lower bound is clear after showing that L-Parish exactly characterizes when a static allocation is feasible. Okay, so with that, I'll stop, ask if we have any questions about our lower bound before we move on to the last component of the presentation, which will be the algorithm. Great. So with that, we're going to step into our last piece, which is going to be an algorithm called using a technique that we call algorithmic guardrails or bang-bang control from the certainty equivalence community, which is going to be our paradigm for achieving this Pareto frontier. I will say that the formal definition for what the Pareto frontier, which is shown on the right-hand side, mathematically is really complicated. But essentially all the algorithm is trying to do is it's going to be parameterized by some value, which we will denote as LT here. And that LT term is going to characterize exactly where along this curve that we just traced off in the lower bounds that the algorithm is going to appear. And this is the exact formula for the Pareto frontier, which again is somewhat unimportant, but included it here just for completeness. So the way that the algorithm works is the first step is we are going to take that construction that we just did, L-Parish. Again, there's a lot of randomness involved. We needed to do concentration inequalities to quantify what that is. But the first step that we're going to do is we construct what we call a Parishchian proof allocation, and we denote it as x lower. And that's going to be b over n minus L-Parish. But wait, n, total demand, is a random variable. And so we replace that random variable with a high probability upper bound on the total demand, which again, we can do using standard concentration arguments. So if we were to allocate this at each period, again, we're not trying to leverage something to improve the efficiency of your algorithm. You could show a performance guarantee that looks like this, where your unfairness scales as the max of 1 over root t in L-Parish, and your inefficiency is root t plus t times L-Parish. The L-Parish term comes from the fact that we are reducing L-Parish from b over n. Similarly, in inefficiency, it's T times L parish because we under allocate by that much at each round. And the 1 over root T term comes from the fact that N, this high probability upper bound, is going to be off by root T on the denominator. And that's what contributes the first term in both of those bounds. So then we have to ask the question is, how can we trade off between worse fairness depending on this parameter LT, which improves efficiency? Obviously, in order to improve efficiency, you just want to allocate more resources, right? But you need to do so cautiously to make sure that you still satisfy some performance guarantee on unfairness, which requires that you don't run out of resources. And so the algorithm then works as follows. So we improve the efficiency by using an upper guardrail allocation. So for a fixed value of LT, we are going to construct an X upper. That's going to be an upper bound for our allocation as the lower one plus this parameter of LT. And so LT, for a higher LT, you're going to allocate even more, which should improve your efficiency over time. And then we need to make sure that the algorithm does not run out of resources. And so in pseudocode, you would allocate the upper amount if allocating this lower amount in the future does not exhaust the budget. Otherwise, you allocate this lower amount. However, this needs to be made formal mathematically, and so the condition looks like this. And so you allocate X upper so long as the remaining resources that you have at time t, your BT alg, is at least NT times X upper. That's from allocating X upper to the current location, X lower to all of the future demand, but the future demand is a random variable, so we need to use a high probability upper bound. And then the last term is kind of the most complicated, which is a measure of perishing that happens under this order X lower and with sigma. And I've written them side by side to make you kind of think back to those tau terms that we described before. The exact mathematical formula for the last term is pretty technical, so I'm not going to include it here. But in the paper, we provide a characterization of what this looks like. And again, it vaguely relates to these tau b terms that we saw before. And so with this, the algorithm is quite simple. And in order to get the performance bounds, the way that you can show it is first for our unfairness bound, we show that unfairness is upper bounded by the maximum of LT and 1 over root T plus this L parish. This happens because the algorithm never runs out of budget. And then by construction of these guardrails, because we're setting X lower, or X upper is X lower plus LT. And so the worst case that it could deviate is by this LT factor. And so that's why you get this potential max. So when LT is sufficiently large, that term is going to increase. And then the inefficiency bound, again, is a little bit complicated. I don't have time to go into the proof. It relates to some ideas around online stochastic packing with guardrails. For those of you who know the profit inequality literature, we end up having to do a switching time type argument. And again, if there's time at the end of the presentation, I can talk more about the proof techniques, but can leave it here for now. Great. With that, we have finished the main segments, and I want to go back to this first slide summarizing the contributions, where we show under these standard regularity conditions on demand, bound and mean invariance. We've quantified this necessary loss due to perishing called L parish. We have these 3 different lower bounds. First one, which characterizes the impact due to demand uncertainty. Second one, which is the lower bound on the product of those 2 terms. That's this y is equal to 1 over x curve that you see here. And the third one is the vertical and the horizontal lower bounds from this L parish term. And we also show that the trade-off is achievable with high probability as well. So with that, I'll ask for any more clarifying questions on the theoretical piece before we kind of go on to some simulations and wrap up. Great. So with no questions, so in the numerical simulations, we asked 2 questions. I want to go to the second one just due to time constraints, where we wanted to try and measure the impact of the allocation order sigma on this, because it's related to some questions that we got earlier on in the presentations. And so as we described in the presentation so far, this allocation X lower and this term L parish implicitly depends on the order sigma. I just didn't explicitly write it down in the notation. And ideally, what you would solve is minimize over all orders sigma, L parish as a function of sigma, right? But sigma is a set of permutations, so that's obviously not super feasible. And so what we wanted to do was kind of test what we thought were different natural orders for which you could allocate the resources. One thing you could try was increasing mean. Another one is decreasing coefficient of variation. And then a third approach would be increasing lower confidence bound. And we tested it under two different perishing distributions, where one had front-loaded variability, one with back-loaded variability. And we saw that this increase in LCB allocation order turned out to do the best. And so as a heuristic, you should order resources by this lower confidence bound, which is the mean minus some standard deviation of the perishing time. And actually in the paper, we have conditions for which this order is optimal. They're a little bit technical, but you can see the paper for more details as well. So with that, we only have 10 minutes left, so I kind of want to provide a little bit of a wrap up and final takeaways. So this paper looked at kind of the practical impact of perishability on an online fair allocation problem. And we actually saw that perishing is kind of more nuanced, both in the probabilistic, but also the optimization perspective. And whether or not these kind of fair and efficient allocation guarantees were feasible really relied on both considering the joint distribution of demand and perishing, because everything got coupled together in this delta term, and also the impact of your perishing prediction order sigma. In terms of relaxation, some things that we've thought about are relaxed notions of fairness. And also more recently, we've been thinking a lot about incorporating stochastic replenishments that I want to briefly mention here, just for the sake of continuing the story. And so there's a kind of natural follow-up question to all of this, which is we looked at two issues. One was demand uncertainty. Second was perishing. But there's also a third issue, which is capacity constraints and replenishments. And I think my co-author Shamsi can speak to this a little bit more personally than I can, which after the LA wildfires, what happened is that people were so incentivized to donate both food, but also like clothing and other goods, that these donation centers had capacity constraints. And makes sense, right? Like these food banks have warehouses that they can't like fill in indefinitely. And so this also kind of creates a challenge because it's kind of a give and take type of situation where you want to prevent both stockouts, which is when you run out of resources, and also overflows, which is when you have too many resources. And so in an updated paper that my co-authors Shamsi and Sid and I also have with Cheeto, who's at Cornell in the computer science department, who's a third-year PhD student, we consider an extension to this model without perishable resources, but with stochastic replenishments. So it's the same kind of vibe. We have stochastic demands, but there's also stochastic supply that happens at each round as well. And there's also a storage capacity. And we do the exact same thing. We consider the trade-off between these two different objectives, unfairness and efficiency, and our goal is to quantify the impact of the storage capacity as well. The main insight is that you get a kind of exponential improvement as a function of the storage capacity. However, it required fundamentally a lot of different technical tools. And kind of going back to this model, I think to some extent what a lot of this says is that resource allocation under stochasticity is important and very important to study. But the fact that we have so many different technical tools, no matter which aspect or piece that you look at, I think means that there's still a lot of interesting insights around a more unified framework to think about these problems more broadly. So with that, I will wrap up and take any questions. I have 3 QR codes here for the 3 different papers that this presentation was on. First one on the left-hand side is the one that did not have perishability. It's the original one. The middle one is the paper that we mostly discussed with perishability. And the one on the right is the model with capacity constraint. So thank you so much. Happy to take any questions.
Yeah, thanks a lot for a great talk. Do you have any questions right now?
I guess I have one follow-up question, and
Hmm.
I don't think you said anything about this. So my naive thought at the very beginning was, okay, like obviously fairness is going to be an issue in these settings, but if we think about like a sequential allocation setting where you have an opportunity to like maybe go to different
Hmm.
places every time as like the
Yeah.
first place, then you can sort of resolve this, right? Like if I randomize, or even if I just shuffle like who I go to first,
Yeah.
then I can make sure that even in the case where the first person gets everything, technically you would end up with like fairness and expectation. And obviously, I
Hmm.
imagine this isn't actually like very practical because it wouldn't necessarily be a very good like allocation scheme if you just, tell everyone here's our route, and then you allocate everything to essentially to the first place on the route, or at least
Hmm.
up to demand, and then but you just like change up who the first person is. I could imagine that not being uh preferred. But I was just curious
Yeah.
how you're thinking about that kind of like fairness in that more sequential setting, and if that relaxation like allows you to in practice to do anything useful, or if that's just sort of like the naive uh computer scientist approach.
Yeah, so that's a great question. I have a PhD student, Haisheng, who's at Northwestern here, who's been thinking about it. But it relates a lot to like the definitions that you're considering for fairness. Do you want high probability or an expectation? Like, are you viewing this in a repeated setting? Where's the expectation in reference to that max? Like, there's obviously a distinction between max of expectation versus expectation of max, right? And Will Ma and some co-authors actually as well has a really interesting paper relating a randomized schedule version of this model to OCRS, online contingent resolution schemes. I think I nailed that. Um, where essentially they show that you can do better in a certain definition of unfairness measured ex ante by doing exactly what you said, which is just kind of flip-flopping back and forth with respect to your orders, right? So you go through forwards and then you go through backwards, right? Um, I think the other thing kind of related to your question is like everything that I talked about today is not incentive compatible. And there's also questions around that of like, okay, if you design your mechanism or you told people that you're gonna go frontward, backwards, right? Is that potentially going to impact people's behavior as to where and which location that they're going to go to? And the answer from looking at the data is that this does happen mildly. Um, and so I think that like all of these things are really interesting questions as well that this is just touching the surface upon.
Cool, thanks.
Yeah, and I wish I knew the exact title for Wilmot's paper, but I can email it to you after. Um, but he talks about this explicitly in terms of the randomized routes.
Okay, great.
Great.
I guess if there is no other question, I think we can end it here. It's like almost 2 p.m. So yeah, thanks again, Sean.
Yeah, thank you so much.
Yeah. And that was our last talk of the semester. So I will send everyone more information about when the seminar series is going to resume, like sometime in January. Probably going to resume everything after all of the January, early February deadlines, like ICML, FACT, EC, all that stuff. But yeah. All
Yep.
right. Well, see you guys next semester. Bye.
Yep. Thank you. Bye bye.